working backwards from velocity. Let's check it out. All right, so the table above shows values for velocity in meters per second. We'll take note of those units. And the particle is moving along the x-axis, meaning left and right. Let's see, what does the value of the integral from 0 to 18 of v of t represent? So if we were to actually calculate this, get a number, what would that number mean? Go ahead, Daniel. Dan?
Distance after 18 seconds.
Okay, so this is your displacement after 18 seconds in what unit? Displacement or distance? Meters. Okay, so from wherever you started at 0 to wherever you started at 18, okay, your position, that is, whatever the value of the integral is representing how far you've traveled from that starting point, whatever it might be, displacement. Perfect. What if we had absolute values on that velocity function? I know it's not part of the question, but what if those absolute values were in there? What would we change about our response? All right, because maybe this particle is moving left a little bit, then right a little bit, left a little bit, right a little bit. Maybe it changes some direction. All right, what if we throw in the absolute values? Yeah. Right, we would, instead of writing displacement, it would be total distance after 18 seconds in meters. Okay, so one little change. Those absolute value bars change every negative value positive, meaning any negative movement to the left is now becoming a positive value for you to just calculate the distance. Perfect. All right, using a left Riemann sum of 6 subintervals of equal length, estimate this value. So we're going to estimate the displacement this particle had over those 18 seconds. So can we section off the chart into 6 subintervals of equal length? Let's see, 1, 2, 3, 4, 5, 6. And we want a left Riemann sum. I see pencils moving and calculators going. It means we're calculating something. Do we got to talk about how to set up that left Riemann sum, or are we good to go? Want to go over it? Yeah? Okay. So let's go ahead. We're going to find the area of this first rectangle. Area of rectangle is base times height. The base of your rectangle is 3, because we have a change from 0 to 3 seconds. And then the height of that rectangle is going to come from the left endpoint. So notice how the left endpoint of your triangle is at rectangle is at time 0. The height, aka y value, would be 2.3. So you're going to repeat that process for all of your other rectangles. The next rectangle has another base of 3, and using the left endpoint, you would have a height of 2.7. Okay, so we're going to go through the rest of the rectangles, add them all together, and we'll get our approximation for the displacement. Okay, how far this particle is from where it started. Anybody get it? The approximate displacement using the left endpoints. 33, sounds good. 33 meters. All right, so this is just an approximation, okay, roughly around that amount. Maybe we'll use a different type of rectangle. Okay, we'll use a right Riemann sum. Still 6 intervals. All right, so if you look at your table, we're still going to use kind of the 6 little things I drew at the top. But this time we want to use a right endpoint height. So our first rectangle has a base of 3, and the right endpoint has a height of 2.7. The next rectangle would also have a base of 3 and a right endpoint of 2. So go ahead working through it. We'll get our approximation for this right-handed sum. It should be close to 33 after all. So maybe you can check your work that way. Anybody get that one? The displacement using the right-handed endpoints? Go, Stevie.
32.4 meters.
I like it. All right. Again, that's another approximation. Let's go ahead and see if we can figure out maybe a different approximation. So for part D, we want to use a midpoint, this time with 3 subintervals. So I'm going to go ahead and erase the 6 at the top that we did. We got to break that chart into 3 sections. Right, so using these 3 sections, the first rectangle has a base of 6 units, and then the height is going to come from the midpoint. So what would that be for this first rectangle? The height at the middle, based off the table, 2.7. Yep. All right, if we keep going, the next rectangle would have another base of 6, but a midpoint height of 1.3. And then you have one more to do. Go, Stevie.
Got 34.2 meters.
I like it. Are we getting these numbers as well? All right, these are all approximations. We don't know what the exact displacement is, but at least we're getting some type of an idea. All right, let's try a different approximation. We'll use trapezoids, 6 intervals again, so we don't have to erase the ones from the midpoint example. What's our area formula for a trapezoid? Kind of the tricky one. Yes, Evie?
1/2 of the height times base 1 plus base 2.
All right, so taking a look at your table, what can we label as the height of this first rectangle, or trapezoid, rather? What? Not quite 3. 6, right? You go from 0 to 6. Okay, so the height would be 6. And then we need the sum of the bases. So based, or looking at this first rectangle section here, what would the 2 bases be?
6 sides.
Did it say 6?
Yeah.
Oh man, we got a... So you were right with 3 before. We're going to erase that. Let's do our 6. My bad. Alright, so our first rectangle, trapezoid, from 0 to 3, base would, or height would be 3, and then the 2 bases, that's a little bit easier to figure out then, 2.3 and 2.7. Alright, and then you got a bunch more to do since they want 6 of them. 3 would have been easier. What about these trapezoids? What do we get for our displacement? Are we there yet? Do we need more time? I know it's a lot of numbers to type in. Where'd you go, Joseph?
32.7.
I like it. Make sure you can get it. Is that kind of coming back to us when we did left endpoint, right endpoint, midpoint, trapezoid? Alright, good. Let's try the last one. Find the average acceleration of the particle from 3 to 9. What does that phrase, average acceleration, mean? What should we be trying to kind of calculate here? Average acceleration. Good, Dan?
You want the slope or change over time of the velocity.
Slope of velocity over time, meaning between 2 points. Okay? And they're giving you 2 points. Yeah.
You can use the E minus FA over B minus A in order to calculate that from the 2 points in the table.
There we go. All right, so we're going to use the time 3 and the time 9 from the table, and we're going to utilize those 2 points to find the slope. So if you're going to write it out mathematically, that would be v of 9 minus v of 3, okay, your changes in the y's, over 9 minus 3, aka the changes in the x's, or t's for this case. So based off the table, the velocity at 9 is 1.3, velocity at 3 is 2.7, 9 minus 3 will get 6. So using your calculator, what can we write as the average acceleration over that time period? With units, because we know what those are. I like it. Meters per second squared. Right, they're asking you about an acceleration, so you need a squared unit on that time unit. Can we get that? Check out. All right, there's another part to this. Let's see. For what value of t in the table is this average acceleration approximately equal to v prime, the slope or derivative of v? What do you think, Dan?
I said 6.
Why?
Because if you look at 6, it is 2.0. And if you look at the next available given thing, which is 9, is 1.3.
Yeah.
Which, if you multiply the acceleration by 3, you get negative 0.7, which is how much it decreases by over that span. From 2.0 to 1.3 goes down by 7.
I get that. Okay. Not sure. Did anybody else get that as well? Never would have thought of it. Okay. Let's think about it this way. We found the slope between this point and that, or you can't see it. We found the slope between this point and this point, correct? if you find the slope between 2 points, isn't that one way of approximating a derivative? For instance, if you wanted to find the derivative at 6, wouldn't you pick a point before it and after it and do slope? That's one way to approximate a derivative. So by finding the average acceleration between these 2 points, that's another way of approximating the derivative of the point in the middle. We've done that earlier this year. So that's another way you might be able to get 6. So we'll say times 6 because by using time 3 and time 9 for the slope, this approximates the derivative of velocity at time 6. Okay, we picked a point before it and after it. All right, we're going to add one more question on the back of that page. So if you want to, go ahead and draw a little arrow, say part G on the back, just because I ran out of room. All right, so part G on the back. Go ahead and take a second and write it down. We're going to talk about what does the integral from 0 to 18 of the velocity represent, but this time we're going to multiply it by 1 over 18. So it's a slight change to the other approximations that we found. Okay, so what does this mean in the context of the problem? And we're going to use units. Do you have an idea, Dan?
Yes, I do.
What do you think?
Well, if the area of the integral is the total displacement, basically, then that's going to be the displacement per second, because it's 8. You're dividing by 18 basically, and there's 18 seconds.
Okay, so let's take a look at this. Notice how this denominator is specifically 18, and 18 happens to be the difference or the amount between 0 and 18, which are your bounds here. Okay, that's not some coincidence there. We already know that the integral piece is displacement. That was the first question we answered. But if we take displacement and essentially divide it by time, remember this was 0 seconds to 18 seconds, you're getting some displacement unit over a time unit, like meters per second. Does that make sense? Displacement over some type of time. Let's think about it this way. Maybe you don't want to write that down, but that's exactly what's going on here. If we work backwards from velocity, what function does that represent? Position, right? And we got to do top bound minus bottom bound according to that fundamental theorem. So we get position, the position of 18, minus the position at 0. That's what the integral represents. We've done and talked about that before. But if I throw a 1 over 18 in front of the integral, I got to throw a 1 over 18 in front of those position values. What you do to one side, you do to the other. So rewriting this, instead of having 1 over 18, we could have P of 18 minus P of 0. Okay, that's your displacement, a change in position, essentially over 18, which is the same as 18 minus 0. This is slope, right? Change in y's over change in x's. We have change in position over time. This is your average velocity. Right? If you find 2 points on position and find the slope, that's your average velocity. Just like the last question we did with average acceleration. If you find 2 points on velocity and find slope, that's going to give you average acceleration. So this is your average velocity in meters per second. We have a position, aka displacement unit up top, divided by a time unit down below. So normally, working backwards from velocity gives you position, but by multiplying by 1 over the time unit, you're changing position back to velocity. It's basically whatever function you're starting with here, that's what you're representing in the end. Normally, we're used to getting position when we work back from velocity, but this number is special because you're dividing by whatever that time unit was. We're going to talk more about this in a future section, okay? But I'm hoping if we think about it, if we work back from velocity, we get position, but we're dividing by some time unit. Position divided by time is another way to represent velocity. Okay? Okay, well, we'll talk about more about that in the next section. All right? How are we doing with working backwards from velocity? That's all what this section was about. Okay, integrating velocity, interpreting what it means. Okay, change in position, aka displacement. If we have absolute values, it means total distance. Okay, that's it for this section. Tomorrow's going to be a free response day, so you're going to be working in your groups, working through some of those problems. The rest of today, though, you can use to help work through some of the homework problems from this section or previous ones. Okay, so maybe make use of that time, ask questions if you have to, but the period's yours, so make sure you use it wisely. Okay.
There goes my wall.